Hello everyone. So in this video we will discuss about the iterative post-order traversal of a binary tree. So in our previous videos we discussed about the recursive post-order traversal of a binary tree, and in this lecture we will see the iterative approach to traverse the binary tree using the post order. So here you can see, let's say we are given with this binary tree and we want to traverse this binary tree using the iterative post-order traversal. So in our previous video, when we discussed about the recursive approach to traverse the binary tree, we discussed that in order to traverse a binary tree using post order, what we do is, before visiting the root, we visit all its elements on the left subtree, then we visit all its elements on the right subtree, and then we actually visit the root. And usually these three steps we perform on each and every node of a binary tree when we do the traversal in a recursive way. So in case you want to learn more about that, you can watch my previous video. So the only thing we need to remember here is, when we do post-order traversal, on every node, we need to first traverse all its elements on the left side, then we need to visit all its elements on the right side, and then we can actually visit the node. So for example, if we are on node 2, then we can't directly visit the node 2. We need to visit first the node 4, then we need to visit node 5, and then only we can visit the node when we are performing the post-order traversal. So in this video we will discuss the iterative approach where we are not performing any recursion. So when we perform post-order traversal using the iterative way, we usually take the help of a stack. So stack is nothing but a LIFO data structure, which means last in first out, where the last element inserted will be the first one to be removed. So we will use the stack data structure to traverse this binary tree using the post order traversal. So let's see the demonstration of this algorithm step by step. So at the first step, what we do is, we create a tree node current which simply points to the root. And in the middle of this algorithm, we are also creating one temporary tree node. We will see their advantages later in the algorithm. So in the first step, we are simply creating the current and pointing it to root. Then we are actually creating the stack data structure. So this is our stack data structure, and we are using the stack class present in Java. So as we want to perform this post order traversal, we need to visit each and every node of this binary tree. And as we are following an iterative approach, we are providing a while loop where we are providing the two conditions. First is the current is not equal to null, or stack is not empty. So here you can see current is pointing to a node having value as 1. Therefore this condition comes out to be true because current is not equal to null. So the overall condition of this while loop comes out to be true, because any of this condition if comes out to be true, this while loop will execute. So here you can see, in the first step what we are checking is that if current is not equal to null, then we simply go inside this if block, or else we perform this logic. So why we are providing this condition here is, let's say current is pointing to a node having data as 1, and let's suppose we want to visit this node. So if the current is not equal to null, then we can't directly visit this node. We need to first visit all the elements of its left subtree, and then we need to visit all the nodes of its right subtree, and then only we can visit this node. So current will be null at this location, and when current will be null, then we can simply decide that now can we visit the node or not. So here, as current is not equal to null, so there can be a possibility that this node has a left subtree. So what we do is, we simply push node 1 into the stack, and then we simply traverse to its left by assigning current's left to current. So current is pointing to node 1, its left is pointing to node 2. So now current will point to node 2. we again check where current is equal to null or not. So current is not equal to null. So the first condition comes out to be true, and we don't evaluate the second condition because of this OR operator. So this while loop will execute. We check whether current is equal to null or not. So current is not equal to null. So this condition also comes out to be true because there can be a possibility that node 2 has a left subtree. So what we do is we simply push the current on the stack. So 2 will be on the stack, and then we simply visit current to its left. So current will now point to 2's left, which is 4. And similarly, current is not equal to null. So this condition comes out to be true. Here current is not equal to null because it is pointing to node 4. So we simply push current onto the stack because there can be a possibility that there is a left subtree or a right subtree. So 4 is on the stack, and we go to its left by assigning current's left to current. So current will point to its left, which is null value. So friends, here you can see now current is actually pointing to null. Now if the current is pointing to null, so this null can be on the left side of this node or on the right side of its node. So if the current is on the left side of the node, then we know that we need to visit the right side also before visiting this node. But if the current is on the right side of the node, then we know that we have already visited left, we have already visited right, now we can visit this node. So in the post order we discussed that in order to visit any node, we need to visit all its left children, then we need to visit all its right children. So if current is pointing to a null, then there can be two possibilities, that this null value can be on the left side and this null can be on the right side. So if the null is on the left side, we need to visit the right subtree for this node. And if the current is on the right side, then we know that we have already visited left and we have already visited right. Then we can simply visit the node. So here current is equal to null. So this condition comes out to be false. But our second condition, the stack is not empty. So this condition comes out to be true and overall condition comes out to be true. So while loop will execute. This if check will fail because current is actually pointing to null. So now we'll go to the else part. So in the first step what we do is, we create a temporary variable and we assign a value stack.peak.write. So here you can see in the stack, whichever is the last element inserted is the peak of the stack. So when we do stack.peak, we are simply pointing to this node 4, and if we do .write, then we are actually pointing to nodes right. So here this is 4 and right will be null. So we will see why we are creating this temporary variable. So for timing you can see that temp is pointing to null. Now here we are given two conditions, that whether temp is equal to null or temp is not equal to null. So why we have provided this condition is because, let's say if current is pointing to null, then we need to somehow check that whether this null value is on the left side of node 4 or on the right side of the node 4. So in order to verify that thing, we created this temporary node. So as current is pointing to null, so this can be any left or right child of a node. And we also know that this node will be already present on the stack. And if we want to know that whether we are on the left side or on the right side, what we do is, we simply go to this node and go to its right. So here temporary variable is doing that for us. So here why we are providing this check here is if temp is equal to null. So this will signify that whatever the value was on the stack, its right is actually pointing to null and there are no nodes left to be traversed on the right side of this node. So what we can simply do here is pull this element out because we are now sure that as current is pointing to null and temporary is pointing to null, which means that we have traversed the left subtree and the right subtree for this node. So now we can simply poll this node out and we can simply visit it. So we'll poll this element out, and now temp will point to 4. And in the next step we'll simply visit the temp. So we are simply printing the data of the temp, which is 4 here. So friends, why we actually do all this stuff is when current actually reaches to any null value, then we need to be sure that whether it's on the left side or on the right side. So we simply create a temporary variable to simply peek the right side of a node present in the stack. And if the temp is equal to null, then it simply signifies that there are no nodes on the right side and we have already visited the left side. So now it's time to visit the actual node. So we have visited 4 here. Moving ahead. So friend, now here we provide a while loop. And why we have provided a while loop? Because the first thing we are checking is stack is not empty. So as we have recently pulled an element out of it, so there can be a chance that stack becomes empty. So stack should not be empty. And the second condition is very important, which is the core of this algorithm. Is we are simply checking whether temp is stack.peaks right. So here you can see, so as we have recently visited this node here, so there can be a possibility and we need to be sure that whether this node is on the left of 2 or on the right of the 2. Because if it is on the left of 2, then we can't directly visit 2, we need to go to its right and visit node 5. But if it is on the right side, then we can simply visit the node 2. So here stack peak is node 2, this, and its right, which is this value, is node 5. So we are simply checking whether this node which we visited just now, its value is equal to its parent's right or not. So if this value comes out to be true, then we know that parent right is actually the node which we just now visited. So we can simply visit the parent now. But here you can see temp is pointing to 4 and stack peak, which is the node 2, is pointing to right. Therefore they are not equal, which means that whatever the node we have visited just now, it's on the left side, not on the right side of node 2. So this while loop will terminate and our call will reach to this while loop again. So friends, here why we have provided this while loop, it will be clear when we reach here. So for timing, you can just think that we have provided a while loop here. So moving ahead, here you can see current is pointing to null, but stack is not empty. So the overall condition comes out to be true. Current is equal to null. So we go in the else. Now in the first step, what we do is we simply assign the stack peak's right value. So stack peak is node 2, this node, and its right is node 5. So temp will point to 5. So friends, why we are assigning this value now here is, as current is pointing to null and we have recently visited node 4, and we also verified here that node is at the left of 2. So there can be a possibility that node 2 might have a right subtree, and in post order traversal, after visiting the left part, we need to visit the right part, and then only we can visit the parent. So here we are simply assigning the value of stack.peak.right. So 2's right is 5, so temp will point to 5. And here we will check whether temp is equal to null or not. So here temp is not equal to null, which signifies that the right part, there is a node which also can have left and right children. So, and we can't directly visit this node because there might be a possibility that it contains left and right children. So here, if this condition comes out to be false, and we go in the else part, where we'll assign the current to the temp. So why we are assigning current to temp? Because this 5 can be treated like any other node which can have the left and right children. So as we started by pointing current to root, it is similar to that step that this node can have a left or a right children. So we need to perform all those steps again on this node. So here current is not equal to null. So this condition comes out to be true. And if the current is not equal to null, so this is the same case which we discussed here, that current is not equal to null. There can be a chance that this node have a left children. So what we do is, we first push the 5 on the stack and then we go to its left by assigning current's left to current. So current will point to null. So as current is pointing to null, so this condition is false. But our second condition is true because stack is not empty. And here you can see current is equal to null. So this condition also comes out to be false. And we go into the else part. In the first step we are assigning stack peak's right value to temp. So stack peak is node 5, this node, and its right is this value. So we are assigning null to temp. And then we are simply providing this check because if temp is null, then we know that current is already pointing to null, which is the left part, and temp is also pointing to null, which is the right part. So which signifies that its parent has no left and right children. So we can simply visit the parent now. So in the first step what we do is, we poll the topmost element which is the node 5 and we'll assign it to temp. So first this will poll out and temp will point to 5. So we can safely visit this node because we have already visited its left and right children. So 5 will be visited here. And then we are providing this while loop which we will discuss when we reach here. So just for timing, think that we are providing this while loop to check whether the node which we have visited is on the left or on the right side of its parent. So currently stack.peak is 2, which is parent to 5. And if we see here, dot right is this value only. And temp is also pointing to this node. So this condition temp equal stack.peak.right is actually true because we are on the right side of the parent and we have already visited this node. So now we can simply poll this element out and we can simply visit because we have already visited its left part and the right part. So this while loop condition will come out to be true. We are polling 2 out and temp will point to node 2. And then we are simply printing the data of this node by visiting it. So 2 will be printed. So as it is a while loop, we are again checking that whatever node we visited just now, is it on the left side or on the right side of its parent. So the first condition is stack should not be empty because we have recently polled an element out. So there can be a possibility the stack is empty. So here stack is not empty. And the second check verifies that whatever the value we have here, which is the parent to this node. So here we are simply verifying that this temp is on its left or on its right side. So temp is actually on the left side. So this condition comes out to be false. So our execution point reaches to this while loop, where here you can see current is equal to null, but stack is not empty. So here current is equal to null. So this condition comes out to be false. In the else part, we will assign stack.peak.right value to temp. So stack.peak is 1 and its right is node 3. So temp will now point to node 3. Moving ahead, we check whether temp is equal to null or not. So temp is not equal to null. So this condition comes out to be false. So if this condition would have come out to be true and temp would have pointed to null, then we could have visited this node directly. But as temp is not equal to null, so there can be a possibility that this node can have left or right children. So we simply go to the else part and we assign the value of temp to current. So now current will point to this node because we have figured out that there can be a possibility that 3 can have left or right children's. So current will point to 3. So now this is the same situation which we saw in the start, that current is not equal to null. And if current is not equal to null, there can be a possibility that there could be a left children of it. So we are simply pushing the current onto the stack. So 3 will be on the stack. And then we go to its left by assigning current's left to current. So current will now point to null. So as current is equal to null, but stack is not empty, this overall condition comes out to be true. So we check whether current is equal to null or not. So current is equal to null. So in the else part, we will assign stack's peak right value to temp. So stack peak is node 3 and its right is 6. So now temp will point to 6. And here we check whether temp is equal to null or not. But here you can see temp is not equal to null. So there can be a possibility 6 can also have left or right children. So in the else part, we simply assign current to 6. Current is not equal to null. And in the if check also, current is not equal to null. And there can be a possibility that 6 can have left children. So we push 6 on the stack. And we go to its left by assigning current left to current. So current will point to null now, which is the left of 6. Current is equal to null, but stack is not empty. So this condition comes out to be true. And overall condition comes out to be true because of this OR operator. Here the if condition comes out to be false because current is pointing to null. And then we simply assign stack.peak.right to temp. So stack peak is node 6, this node, and its right is this node. So temp will now point to null. And here we are providing this check that if temp is equal to null, which means that current is pointing to null, and whatever its parent is, its right is also pointing to null. So we can safely visit this node, which is the parent. So how we can safely visit that node is, first we'll pull that element out of the stack. So 6 will be pulled out and temp will point to 6. We will visit this node. So 6 will be visited. Now friends, here we encountered a while loop and we discussed that why we are providing this while loop is because the first check is stack should not be empty. So stack has 2 nodes, therefore it's not empty. Now as we have recently visited this node, so after visiting this node, we need to be very much sure that whether this node was at left or was at right to its parent, which is 3. We can access 3 by stack's peak, which is by getting this value. And if we call dot right, then we'll reach here only. So if temp is equal to this value only, then we know that we are actually on the right side of temp's parent, which signifies that we have already visited the left part, we have completely visited the right part, and now we can simply visit the parent. So here we pull the parent out and temp will point to 3. We visit 3 and we again encounter the while loop. So friends, here you can see that this while loop is provided because if this is the condition here, then here you can see that stack is not empty. And as we have visited 3, so this 3 can also be the right child of its parent. So therefore we are providing this while loop. Let's say if this chain goes on like this and there are no left nodes, so this while loop will simply make us traverse back, because all these nodes are on the right side of its parent, which we already visited. So that's why we are providing this while loop. So here again we are simply checking whether temp is pointing to its parents right or not. So here stack.peak will give us 1, its right will give us node 3, and temp is also pointing to node 3. So this while loop condition will come out to be true, and we can simply poll 1 out, because we have visited all the left subtree of the node 1 and we have recently visited all the nodes on the right subtree of 1. So we can simply poll the 1 out. Temp will point to 1 and we can simply visit node 1 now. So node 1 will be visited here. And finally we again check whether stack is empty or not. So here you can see we have recently polled one element out. So stack is empty. So this condition comes out to be false and the while loop will terminate. And once the while loop will terminate, our call will reach here. So here you can see current is equal to null. This condition is false and our stack is also empty, which signifies that we have completely visited this binary tree using the postorder traversal. So this whole condition will come out to be false. So friends, here you can see that using a stack, we visited all the nodes of this binary tree using the postorder traversal. So this was the sequence. First 4 was visited, then 5 got visited, because before visiting 2, we need to visit its left part, then we need to visit the right part, and then we can actually visit the node. So 2 was visited after that. Now we can't directly visit 1 because we need to traverse all the nodes of its right subtree. So we reached here. We saw that 3 didn't have any left part. So we can't visit 3 directly. We went to its right. We saw that 6 left and right both are null. So we simply visited 6 then. After we visited 6, which was on the right side, we safely visited 3. And 3 was also on the right side, so we safely visited 1. So this is the postorder traversal of a binary tree. So friend, this was all about this video, and in case you have liked this video, then please like, comment, share and subscribe my channel. Thanks, have a nice day.